Hi, my name is Brooke. I'm the founder of the Santa Barbara Blockchain Institute. Our mission is to provide Bitcoin lessons for everyone in simpler, easy to understand terms. I have a larger presentation that I've carved up into 10 smaller chunks to allow people to look at them at their leisure and gain a better understanding of this exciting new technology. My website address is down below if you'd like to get in touch with me. That'd be great. We need to grow the network. So today I want to start with what I have developed as my own personal model of Bitcoin and blockchain so I can understand everything that I've read a little more clearly. So first of all, we should talk about disclosures. I'm not a financial advisor. This is not investment advice in any way. Do your own research. This is just an informational educational lecture. Also, I'm not a programmer or a technical expert, so I'm going to try to keep it light and simple to understand here, not going deep into the weeds here. But I do I personally hold digital assets, so I've got skin in the game here. As an overview to lecture 4 about a model, I want to talk about Bitcoin as the world's first self-building and autonomous network, because that will come to play into the model discussion later. It acquired its value all on its own. It's a completely decentralized network around the world, and it runs itself. It's autonomous, and that's really the first time we've seen this. It is the world's largest computer network, and it's secured by the investment of energy, something that we'll come back to at the very end of the lecture. Something called hash rate. Hash rate represents all of the computing power that are brought to bear to secure this network, and I'll describe that in more detail, as I said. But this presents a physically prohibitive cost to attackers. It's a real-life cost if you want to attack this network. You've got to spend the energy to do so. And most of the time you'll find that it's not worth that cost. It would be better if you participated in the network rather than try to attack it. It's these types of incentive structures instead of kind of a command structure that really has served to nurture its growth over the decade plus that it's been around. So let's move on to my model, which is a very simple model, but helps at least to categorize the various things that these protocols do. So at the bottom right, you'll see in green the purpose or use case. And in this case, we know Bitcoin was created to be a peer-to-peer electronic payment system outside of the banks and the governments that often control it to our detriment. And so there will be other purposes and use cases once you come to understand how blockchain technology functions. But we're in the process of this great explosion of ideas and copies and variations that won't all work out. That's become quite clear. So the next category in my model is the consensus protocols, or the governance. And these govern how does the blockchain work in this, given this use case. We call it consensus protocols because in this world of decentralization, everything is done on a peer-to-peer by group basis. So we have consensus. Everybody agrees this is the version of the truth we're going to go with. These are the transactions we'd like to preserve on the ledger. So things are done in a consensus, not in a command format. And so that's talking about the rules of the road for the consensus. The supply distribution operation quadrant in blue there is more simple logistical operation of the blockchain and how transactions are performed, whether there's a limit to the number of tokens and how they're exchanged. So that does become also important with the various other blockchains that have been developed. All of these categories are important. Lastly, security. We're familiar with the security of the internet, which in a word is kind of woeful. It was designed to bring us together, to allow us to communicate and collaborate. It really wasn't there built very well to protect us, as we see, because we're constantly being hacked left and right. And we'll talk a little bit about intrinsic security features as we move forward. So starting out in that left top corner about supply and distribution, just a quick shot of Bitcoin's supply chart. And one thing that makes Bitcoin a little bit unique is that this supply chart of the actual tokens is complete, it's finalized, it's done. It's not going to change for the entire life of Bitcoin. Bitcoin, among other things, has a fixed final amount of 21 million tokens. That's the first time really that we humans have invented or come across something that has an absolutely fixed amount to be created, a limited supply. final supply. If that were to be changed, then tens of thousands of computers all over the earth would have to agree to change it to a new number, and that's just simply not going to happen. So we're considering it to be fixed. You also have to work to create these new Bitcoins, and I'll describe that process a little bit later. But that makes them assets. Similar to gold, commodity, you've got to invest energy in this case to create more Bitcoins. To get more gold, you have to invest in picks and shovels and go out and do work. To invest in creating more Bitcoin, you need to produce more energy to solve a puzzle. And I'll talk about that a little bit more later. At any rate, the neat thing is the supply is absolutely already predefined. There it is, and that's not going to change. And we don't find that characteristic has been copied very many times in the other blockchains that we've seen. But it's an important part to understand in the operation of a blockchain. So I'm going to move around that circle of my model down to security, and we'll have a couple of slides here. Just some quick illustrations to give you some idea of how blockchains function as opposed to just traditional models. So you see under the old traditional model, everything is under one roof. You build a fort and you put your gold in it, you surround it with your soldiers. That hasn't changed much through the millennia. We build a website, we make it as strong as we can and protect it with the softwares, but all of your assets are in one place. So it really requires that you trust that institution and you trust the security that that institution has decided to employ. So when you go to a decentralized mode, there are a couple of things that are different. First of all, your assets are spread out everywhere across the system. They're decentralized. And the second thing is that each one of those decentralized nodes has a full copy of the ledger. You may remember from earlier lessons that a ledger, keeping track of all of the assets, is a super important part of the token world. And so in the decentralized model, every single node has a full copy of the ledger, which makes it pretty immutable, pretty unchangeable. And in addition, all of those nodes are watching the system at all the time, and they cooperate. Now, some of those nodes are special nodes, and they're miners, so they're also contributing to the production of new Bitcoin, but many of them are just observers. Many of them are just watchers. I have a node here at home. It's possible to keep one on a regular small computer because of some of the neat algorithms that are employed. So that's the idea of the strengths of decentralized security. The next image I want you to kind of bear in mind here as we talk about security is the idea of sort of the cooperative, the consensus. So I pictured this clear vault to represent the Bitcoin network. So everything in the network is contained within its clear walls. And people walking around outside, even not in the network, but just on the internet, they can see inside this clear vault, and they can actually even see inside each of the wallets that are inside that vault. And they can then, therefore, they can verify any transactions. The transactions performed by somebody going into the vault. Now, we don't know who it is because those vaults are only identified by a long number string. And so we don't know who that person is. They put on a mask when they go in, like the gentleman there transferring coins. And so they're pseudonymous. They're just represented by a number identifier. When they leave the safety of the vault, they need to remove their mask and they leave into the real world and they become identifiable and identify people. So in terms of security, when anything that happens in the vault basically stays in the vault and all the watchers are constantly watching to make sure that it's verified and legitimate. Where we run into trouble with this type of security is once people leave the vault, they've left the protection of that clear, transparent vault, and they can run into troubles with exchanges, mistakes and or fraudulent exchanges that are outside of this that would be serving to convert those coins into fiat currencies or convert from this blockchain, which is the Bitcoin blockchain, into a different type of coin which lives in a different clear vault. So the other vault may not be quite as clear, it may not be quite as easy or well designed as the Bitcoin one, but this vault has functioned without problems now for 12 years. It's basically proven itself to be unbreakable. And here's just kind of a visual image to help you kind of see in your mind's eye what that security looks like. So it's cooperative. Everybody can see it all the time. On the internet, you can run a Block Explorer and get a report on any transaction that's happened inside that clear vault because it's transparent and visible to all. Now, it's not going to give you names because that's the pseudonymous nature of the Bitcoin security. But you will see the wallets identified, the transaction amounts identified, and the specific times and blocks that these are associated with. So you do have that level of transparency. So decentralization, transparency, these are huge elements for the blockchain that just simply don't exist in our traditional worlds. Also a fixed supply, as we talked about in earlier lessons, that scarcity element of money is hugely important, and we don't have anything else that has a permanently fixed supply. So these concepts you see are all kind of coming together in the form of the Bitcoin blockchain. Another neat concept I like to sort of visualize is this idea of the original and being able to identify an original. We get to be able to do this because our computers now can handle massively huge numbers, and we're talking numbers like the number of atoms in our known universe, which is just an unfathomably large number, but handleable by our computers. So in this instance, I want you to consider that if I write to you a letter, say I type out a letter and I sign it, now it's on an original piece of paper. I can take that piece of paper now and I can make a whole bunch of photocopies of it, tons of photocopies. Then I'm going to tear that piece of paper in half. And I could even put those two halves together and make some photocopies after it's been torn. But there will only be one original that we can easily identify, because in the act of tearing that page apart, I've created a torn edge that simply will not be matched by, no matter how many times you try to tear any of the copies to match that original tear. You can understand just by simple logic that you're not going to be able to make a tear that is exactly the same as my tear. The numbers, the possibilities are just way too large. You know, it might be possible, but it's just not going to happen. And that's the kind of idea behind, say, the identifying numbers of those wallets in that vault. That although it's just a number string, the possibility of somehow being able to duplicate that number and gain access to a wallet is unfathomably small, such that essentially it's not going to happen, and it never has. So I like this image a lot because people can understand once you've torn that, that's it. And it's something that's easy to do in the physical world. We can now replicate this idea online with math and with computers, the idea of tearing an original so that it simply can't be matched. Now the art world loves this because for a long time they've had trouble with the internet world, where we right-click, copy, paste things, and who knows what the original is. The internet is a giant copy machine. But when we put it through a process like this in a blockchain, we can tell that is the only original and the true original. So that's a concept that's more easily visualized with a real-world example. The last concept I want to familiarize you with before we go to actually how the blockchain is created is this idea of a cryptographic hash. Very simply, a hash is going to take an input of any size input information, a bunch of characters, a transaction, anything. It's going to take it, it's going to run it through a computer program, which is basically a one-way little compression function that gives a fixed length output. It doesn't matter how much you put in, it's going to give an output of exactly the same length. And if you put in that same input, it'll put out that exact same output every time. But if you modify anything to do with that input, and you'll see some examples here, if you put a little bit more data, you put slightly different data, if your data is in a slightly different order, or if you leave a little bit out and put in a little less data, any slight modification results in a different output, a different hash. And that's really important because that is the linking part. When we say blockchain, the chain part are links that link together data, and that chain part is super important. This is what the hash is used for, and I'll explain that in the next slide. So people wonder, why is it called blockchain? One of the problems with creating a money is that you have a double spend problem, especially with an internet money. How do you know that that dollar, that digital dollar, hasn't been copied and spent somewhere else? The only real way to do this, and this comes back to Bitcoin being created from the ideas of prior people like Nick Szabo and Wei Dai, early Adam Back, early computer scientists who solved some of the problems, but not all of them. So one way you can stop the double spend problem of an online currency is by cutting your time into blocks. And if something happens within this block of time, you can verify everything in that block is okay. And then you make it impossible to duplicate anything that happened there, to reuse the things there in subsequent blocks. Now you found a way to defeat the double spend problem for money. So we're going to carve time into blocks and isolate transactions in the blocks. The next thing we're going to do is we're going to tie those blocks together, essentially in a chain. And we're going to do that with that cryptographic hashing that we talked about. So this is how it works. The very first block that was formed was because people submitted transactions to the network. They wanted to have these transactions done and they wanted it recorded on the ledger. So they submitted all these transactions into a pool. And the very first miners plucked a bunch of things out of this pool and they put them into a block, this data into a block. So now you have miners spread out around, each with their own version of a block. The next thing that happens is those miners are all given a math puzzle, a problem, and they're given this by the network. And so all the miners who want to use their block that they've created of transactions, they have to work a way to try to solve the problem, this puzzle. If they're the miner that solves this puzzle that's been given to the whole network, they earn the right to make that block a part of a chain of blocks. They get the right to attach their block to the block prior. And in doing so, they also earn some Bitcoin. The amount of Bitcoin that they earn slowly goes down over time, and that refers back to that distribution of Bitcoin tokens that I talked about early on that's so clever and eventually limited. So the miner earns some Bitcoin by solving this puzzle. So the best way to solve this math puzzle is by having the most powerful computer that you can. So miners have an incentive to have the most computing power or hash power possible so that they can solve the puzzle and win the right to attach their block. And that's where we hear the objections from the environmental side of things, where we need to use energy to win the right to attach a block. Now, if you think about the positive benefits from using that energy, it's far superior to something, say, like playing video games or other things, but we'll leave that for a later lesson. The idea here is that the more hash rate that's employed to solve that puzzle, the stronger the network becomes, because the competition among miners is fierce, and that's what keeps the network safe. So the second thing, now that we've carved time into blocks of transactions and we've connected them together, is how do you protect them? And this is where we get to that hashing algorithm. So the very first block that was created, what was done to it is all the transactions that went into it, and you'll see at the middle example of train cars there, all the transactions that were included in that block, all that data was hashed together. And you remember the hashing function then produces an output of a fixed length. So if you imagine that output from hashing all those transactions together was stuck onto the very first block, and that was its block label. Now the next block that came along in time and that was attached, the transactions of that block were all hashed together and then also hashed to the label, the hash of the first block. So the second block's hash, or identifying label, is a combination of all the transactions in it plus the hash of the prior block, and so forth and so on. We repeat that. So as we get a chain of blocks, which is the transaction data, they're linked together by hashing their identifying hashes together and together and together. What this means, as you remember from the description of the cryptographic hashing, is that if any single piece of any data from prior blocks is changed, it's going to immediately change the hash, not just of that block, but also every subsequent block, the hash is going to change because they're all linked together. That's the chain part about blockchain. It's actually a security feature. So blocks of information chained together creates a blockchain. It's actually pretty brilliant. So all the nodes, those watchers that I talked about before, if you go back to the illustration of the network as a clear vault, all those watchers will immediately see on their ledgers if something went funny, because the hash on every single block will suddenly change if somebody tries to tamper with the data, any part of the data in any block. And so that's just a brilliant piece of security written into this system. Now, the last piece that I want to leave you with, and I know we're a little bit into the weeds here with the details, but the last piece is equally important, because now we've carved time into blocks, and each block in the Bitcoin network is 10 minutes long. Incidentally, there are a lot of other things that are in the consensus protocols that have to do with how many transactions can go into each block and the size of the block and so forth. For the Bitcoin network, these blocks are attached every 10 minutes. Every 10 minutes since 2009, another block has been added to the Bitcoin blockchain. How do you ask, how is it that it can be every 10 minutes for sure if the number of miners and the amount of that computing power, the overall hash rate, has gone up? Wouldn't they solve that math problem sooner and quicker and start speeding up the train and adding blocks more quickly? It's a good question, and it's something that Satoshi the inventor thought of. He found a way to adjust the speed of that train too. And the way he did that is on this slide. The system keeps track of how much time has gone by between the blocks being linked together. It has a target time of 10 minutes. So once every 2,000 blocks or train cars, it does a check on the time that it's taking. And if it's taking too long, it makes that math puzzle easier. If the train is speeding up and there are many more miners using a lot more hash power computing rate to try to solve that puzzle, and it's speeding the train up too fast and they're being done in 8 minutes, let's say, then it makes the puzzle harder. So here's a chart that shows as the hash rate in blue climbed and climbed with more miners participating and more computing power being added, the puzzle difficulty also stair-stepped up, and that's the yellow line stair-stepping up as the hash rate grows. Now, the other part is, well, what happens if the reverse happens? So when China banned mining suddenly, a lot of miners had to turn their machines off. Did that hurt the network? Did it suddenly slow the train way down because the puzzle was hard and there weren't enough miners to solve it? No, it didn't, because this difficulty adjustment realized that it was taking too long to solve the puzzle, and it made that math puzzle easier. And you see that's the downstepping here of the difficulty adjustment. So the difficulty adjustment is just one more piece of the brilliance of Bitcoin that really keeps that train running on time, and it has done so effectively for 13 years, even though the hash rate has really climbed and it's taken its occasional dips through the years. We've still kept to that 10-minute cycle. So that is the last idea that I want to introduce to you as you get a bit of an understanding what this blockchain really means and how it functions. Now, as a practical matter, if you're to visualize what this looks like, a traditional centralized finance payment system, such as, let's say, Venmo or PayPal or something like that, it's centralized. It's got a rule-making and rule-enforcing entity or body. Actually, it's got several. If I were to send you a Venmo, the instructions would go to my bank, and then it would go, via the Venmo software, possibly through several other service providers, end up at your bank, and then finally end up in your account. So there are actually a number of different intermediaries there, and each intermediary takes time and has an expense associated with it. When I say it takes time, people don't usually realize that our traditional system actually takes 60 to 90 days for final settlement of any transaction. Any money transaction takes 60 to 90 days. You know, with your credit card, you can do a chargeback or you can dispute. So things can't be final right away because sometimes you get them reversed or changed or fixed. So the truth of the matter is it takes 60 to 90 days to make any transaction in our financial system a final settlement. Even though Bitcoin is sometimes called slow by its critics, we reach a final settlement in Bitcoin as soon as a couple of more blocks have been added to that train, because it becomes impossible at that point to undo things and to reorder the transactions. Once your block of transactions has reached several forward, it's done. So 20, 30 minutes or so is usually enough to be pretty secure about your transaction being final on the Bitcoin blockchain. So the model, what it looks like is a peer-to-peer model at the bottom of this illustration shows really, if I'm going to send you something instead of through Venmo, through Bitcoin, it goes into the Bitcoin network. It goes through the process that I just described as a transaction approved, being put into the pool, being put into a block, being attached to the chain, making its way forward in time and being final settlement. That happens relatively quickly, and there are really no other middlemen in the process to slow it down or to charge us fees. So it's much faster for final settlement, and it's basically free to us to do that. Very, very, very low fees for the system to execute that transaction. That's the basics behind how the blockchains work and the reasons why they're so much superior to our current traditional centralized system with all of its intermediaries and all the time it takes. This is what popped into the heads of people who read the Bitcoin white paper and why it's been able to claw its way into existence, and the tokens have gained value over time. So the next lecture, I'm going to go a little bit deeper into the consensus protocols, because that's another feature of Bitcoin that really sets it apart from some of the other tokens and coins that have been introduced. Like, exactly how does it manage? What is this proof of work, this use of hash power by computers to be the thing that determines what transactions are valid and what should get attached to the blockchain and recorded on the ledgers. So we'll bring that up next time. But if you have any questions, again, please don't hesitate to reach out to me. I look forward to seeing you soon, and thank you for watching.